Hello, my name is Christophe de Dinchin, and it's been a long time since I've made a video update about DB48x, a project that delivers a modern implementation of RPL, Reverse Polish Lisp, the programming language of high-end Hewlett-Packard calculators like the HP48 or HP50. DB48x runs on physical hardware such as SwissMicros DM32 and DM42 or DM42N calculators. You have a DM32 here with a keyboard overlay, and you can find on the project page here a link to how to get that keyboard overlay, which gives you the markings corresponding to the functions implemented in DB48x as opposed to the original DM32 firmware. So this is running an earlier version of the software, and I'm going to upgrade it to 0.9.2, which is the latest. To do that, I use the Shift key here, then Setup, which brings the firmware setup menu, and I'm going to activate the USB disk. And now I'm going to do it like as if I was a developer. So I'm going to install a build that I just finished here as a developer. And so I'm going to type simply make that -j DM32 install, since I'm installing on the DM32 here. And it's copying, it's going to finish the build for some reason. Maybe my build was not clean. Sorry, this introduces a small delay. And then it's going to copy the various installation files over USB to the calculator. So you can see now that it's copying DB50x.pg5. So DB48x ships in two versions, one for the DM42 calculator, and that's shipped as a DB48x.pgm, PGM, and one for DM32 or DM42N. That's essentially the same hardware platform from SwissMicros, and it's called DB50x.pg5 because that's DMCP5. So it's copying the program there, then it's going to copy what is called a QSPI file, a binary firmware, and then it's going to copy a number of help files and support files, BMP files for the help, and so on. The help file is written using the standard Markdown language, and this is the same help file that you find that you find on the website here. So the same online help found in the calculator is also what you're going to see on the GitHub project. This means that the documentation is always up to date because it's really the same content. Now, on that project page, you can find a number of links. As I mentioned, there is a link to order keyboard overlays here. And there is a link to adjust. You can try the project in your browser directly using WASM. And there are links to various videos for presentations that I gave at FirstDem 2023, 2024, and there is a YouTube playlist that lists various videos. So back to the update, it's almost done copying the files. Now it's going to eject the USB disk. So this is the process that a developer would use. When you use the binaries that are shipped on the project page, you simply copy a tar.gz file and then you expand it wherever your volume is for the calculator. So while we are waiting for this to complete, okay, so it's done now. You see that it says that a new key map is installed that is specific to the DB48x. And so now I'm going to press any key and first load the QSPI file using 7. So now it's flashing that to the internal memory. Once this is done, I can restart the system. And the checksum no longer matches, so I'm going to have to load the program using 3, load program, and I'm going to load db50x.pg5, which is the file I just copied. This flashes the firmware to the disk. It restarts once more. Now it reloads the demo state, and I'm running the new version, which is in that case version 0.9.2, which I'm going to verify right away. So to verify the version, I'm going to use the version command, and you can enter alpha mode with shift alpha. Then I can type V, E. I'm trying to not move the calculator too much when I'm doing that. So R, S. And then I'm going to use the catalog by hitting plus, and F1 gives me version. So the catalog auto-completes as I type. If I do this, you see that I have more commands, and when I add the R, version appears, and I can hit F1 to get that. So we have 0.9.2 installed, and you see now at the bottom the catalog of all the functions. Let me drop that. So this is an RPL calculator. You have an infinite stack, and it behaves more or less like an HP48. I'm going to assume that you know how these kind of calculators work. So there I just added 1, 2, and 3, and 1 and 2 to get 3. You have symbolic operations, text operations, and so on. There are a number of demos in the var menu here, which is under demos, as indicated by the text that was loaded. Let me try the first one under physics. And there is a kinetic energy computation. And it's comparing classical and relativistic kinetic energy. The program that does that is, I can recall it. You see that every variable in this memory here has 3 entries, 1 to execute, that's the one I just used. Then if I shift once, I have an arrow on the right to record the value, and shift twice, an arrow on the left to store into the variable. I'm going to record, in that case, the kinetic energy program to see what it looks like. And then I hit, then I hit the right arrow to edit my program, and that's what the program looks like. I can use shift to use the up and down keys. So this is the RPL program that does the drawing we just saw. So now my machine is updated. You see that when a program is a little too big to fit comfortably on screen, it instead simply displays a large program and saying what the size of the program is. The same is true with lists, etc. So if I enter a small RPL program that adds 1, like this, 1 plus, that's going to display on the stack directly. But the other program is a bit too big to fit. And this is something that can be adjusted. There is a setting to say how large you are willing to go for displaying objects. When something is too large to fit, you can use the show command, which is shift dot, to see it in full on screen. So that's another way to see large objects, large vectors, large matrices, and so on. To give you an example of a large matrix, I'm going to use the matrix menu, and I'm going to do a random array with 7 by 7. Sorry. So let me go. It's hard not to move the calculator while I'm doing that. So 7 by 7, and I'm going to hit a random array. So there are soft menus here. I hit F5 for random. So this one is small enough to fit on screen. Now let me do that again. I use the history menu to recall what I had, and now I'm going to enter 17 here and 17. That's not going to fit, I guess. F5 again. And now I have a large array like before, and using show lets me see it on the screen. So I can scroll like this, and in that case, in the show command, I can scroll with up, left, right, and if I shift, it's going to be faster. Okay, so we have seen some of the basics. This is intended to replicate many of the features of HP calculators. One of the features that has been implemented since 0.7.8 is the interactive stack, which you hit by using the up key. And then you can move through the stack. And for instance, you can edit any object on the stack. So I can hit F6 there, and I edit this object. And then I'm moving through. So I did the object, and then I can update any object on the stack that way. And there are other operations like sorting, reversing, and so on. Okay, so as you can see, this is not very practical to do operations like this directly on the calculator. So I'm going to shift to a simulator mostly so that it's easier for me to type. Let me launch the simulator. And the first thing I'm going to do is launch the simulator with, so let me shift to the simulator. So you see the simulator with the same state, but now it's easier for me to do the operations that we saw. For instance, if I want to type version, I can type like this. Sorry. So I type VER plus, oops. So I said it was easier. VER plus, and then I have the version here. And so this is the one I just built, which is Z430, because I just built it on top of 0.9.2. Okay, so one of the things I can do with the simulator is run a test suite, hitting F12, and then it's going to enter an automated test suite. And I did not think ahead with, so it doesn't display right. Let me shift like this. Just trying to resize. I'm resizing things live, which is not very smart on my part. So this is simply to show how the calculator firmware is actually tested before being shipped. There are about 5,200 tests at the moment, that are being run automatically like this. Some of them include random data that varies from one run to the next, like the computations on integers and so on. So the whole test suite is going to take a couple of minutes. It takes about, depending on the machine you have, it can take 15-20 minutes. So we're not going to go through all of it because what is interesting is seeing what are the features in the calculator instead. Now, what you're seeing on the simulator, another thing you may observe is that the simulator is actually using color. And so it has a color display. This is also the case for the DB48x application on the iPhone. Soon coming on Android as well, I hope. So let me just interrupt for now the testing by hitting F12 again. And so now we are going to explore a little bit what's new since 0.7.8. So one of the first things that we completed was the equation library. I had a lot of help from a Canadian physicist called Jean Wilson. I don't know how he says his last name because I think he's French native, but Wilson, I'm not sure. So in any case, we hit this equation library using Shift and the F key. And you see that you have categories of equations that correspond for the first ones to the categories in the HP50G itself. So let me show you with the manual of the HP50G where we are going to look for the equation catalog, which is close to the end. Let me format. So you have here the catalog of constants. We also have support for all these constants and way more in the DB48x. Okay. It's simpler if I search. Okay, so this is the equation reference from the Advanced Reference Manual. And so you see that you have columns and beams and electricity, fluids, force and energy, etc. And you're going to see the same kind of menus here. So you see, you recognize the columns and beams, electricity, fluids. There is another one, physics, that was not there on the original. So if I go to columns and beams for instance, like this, hitting F2, then I have the various equations, elastic buckling, and so on. And what is different compared to the HP calculators is that there is a complete help for each of these equations. So let me look at elastic buckling. I hit the F1 key and I maintain it, I hold it. And that's going to invoke the help for it. And you see that the online help includes diagrams. And it also, it explains a little bit what this is about. What are the variables that are used in the various equations. So essentially, it's an adapted version of what is in the manual for the calculator. Let's compare with what we have in the original PDF from HP. So you see the columns and beams from the HP manual here, and you recognize that you'll have more or less the same text, but now it's directly inside the calculator, so you can use it. You can use it directly as a reference. So you have the variables there, and we're going to go down in the calculator and explore a little bit. And what is interesting also is that you see this gray text here, and that's an example. Now that example is a replica again of a similar example in the manual. So if you look carefully, you see the example says given blah blah blah, and it uses a similar format with L equals etc. But the difference is now if you click, if you hit enter, you're going to copy that in the editor, and now you have the example that was given entered as is with the expectations. And what is interesting is that you will notice a command that says expecting blah blah blah, and this is actually tested by the test suite. So it's checking that it's getting this result. And then it shows you an example of programmatic resolution of this problem. So I hit enter. Now, if you're familiar with HP calculators, you may not recognize this kind of object here, E equals L equals. So what this is something called an assignment object, and we are going to use it while doing our equation solving in a moment. But for now, let's just say that it sets the initial values, and it sets the initial values in the variables. So the value of I, for instance, is what was specified over here. Now, what was it specified in level 2 here? Now let me evaluate that command here. So I hit the eval space key at the bottom right, and I'm going to evaluate the solution for this, and it gives me PCR and sigma CR, and you can check that these are similar values to what is found. It's not exactly the exact same values as what the HP calculators find, simply because we are computing with 24 digits, whereas HP calculators compute with only 12. Now, what is interesting is that you have this vector of values which are themselves assignments, and you can change parameters. So let's say I edit this with F6, and now I edit it as 0.5. And if I evaluate that now, so let me just first check the value of the variable. So we edited K. So if I look at K now with F4, the value of K at the moment is 0.7. Now if I go to this K equals 0.5 here, and I evaluate it, it stays in place. It evaluates as itself, but now the value K is 0.5. So I can quickly do various iterations like this and explore my equations with various values. Let me use the history menu with Shift left arrow, and I can then use the F2 key to cycle through, and then I'm going to hit select and delete all that stuff because I'm really interested in that part. Let me solve again, and now with a different value of K, you see that the values have changed, and so I can quickly explore through my equations that way. Now, if you have questions about variables themselves, you see that, sorry, let me get back to my equation menu. So with F, Shift, and the F key, which is on the top right of the keyboard, and I was in columns and beams, and I was in the elastic buckling solution. Now, I can also do the same kind of operations I was doing, but now in a programmatic way. So let me just erase everything on the stack. And I'm going to shift twice, select F1, and now that enters the interactive solver for that equation. So I see the equations in the system, and maybe more than one. In that case, I think there are 4 or 5. So let me go through. I'm going to cycle through the equations with next EQ. And now I can decide the order in which I'm solving. So for instance, let me say that I want a PCR of 1300. So I can do 1300. And then 2 is going to keep the same units. And you see that it memorizes that with an assignment object. That means that I have on screen the values that have been set. And I can, using the same trick of going there and evaluating with the interactive stack, I can have multiple values that I can test with. So let's say I can also test with 1305. And now alternating between these two values is as simple as going there or there and then hitting F3 to select one or the other with eval. And then my value for PCR, you see, is 1300 there. And now I can solve for K using the label with a question mark next to it, so with one shift, and then F5. And now I'm solving for K, and I see that with this value of K, I'm going to get 1300. So I can solve all the equations interactively like this in any order. I can essentially decide which variables I'm solving for. So this is really the equivalent of the HP50G multiple equation solver, but as you can see, it has many improvements like assignment objects, online examples, and the ability to display the equations as you're progressing. Now, once you have solved, you can use eval a Q like this to get an idea of how accurate that is. That preserves the units, the engineering units that were in the original equation. So now you have a comparison between kilonewtons on the left and another unit on the right, and you see that the equation was solved to 1 to the power 1 times 10 to the power minus 16. So it's a relatively good result, and I'm really close to having solved the equation there. Okay, so this is for the equation library, and as I mentioned, it's really extensive now. We have almost twice as many equations compared to the HP50G, which already had a pretty extensive library. So among the improvements compared to the original, let me go back to here. And if you see, you have improvements in optics, but you have also things like nuclear physics, modern physics, and so on. So let me go to relativity, for instance. And you see that you have all the relativistic equations, time dilation, and so on. And you can solve for, so let me solve for time dilation here. And again, if I want to have information about the variables, I hold F2, I maintain it held like this, and this tells me that delta TP is the dilated time interval in that equation. So it's really, I think, a nice and convenient way to explore modern physics, modern mathematics on a calculator. Now, if I want to know about, so you notice that many of these equations have units in them and refer various constants like c, the speed of light, or things like that. So there is also an extensive catalog of constants, which is the equivalent of the HP50G constant library. And now I'm going to access that with the const menu, which is the left. So yellow function, so shifted once on the I key or stack. So I do this, and now I have a catalog of constants that are also, as you can see, sorted by category. And same principle. So let me go to physics, for instance. And now I have the speed of light c. I can hold c to have documentation about the speed of light and what it means. And I can hold shift and get its numerical value directly. And I can do verifications, like for instance, I can take epsilon 0 and I'm going to take the square root of that. and the inverse of that, and take the numerical value. So to get the numerical value of that, I use the toNum function, which is the shifted value on 1. And so now this is not in the exact same units, but I can use the ubase menu, which is in the unit menu, ubase function, sorry, the conversion menu, which is the blue value, so shift twice on 5. And I'm going to take the base unit for that, and you see that it's the same value. So this is the famous equation epsilon 0 mu 0 C2 equals 1 is verified on the calculator. Now what is interesting with the constants in DB48x is that they have all been updated in 2 ways compared to the HP50G. The first is that we now have constants that are up to date according to the latest CODATA information that we could gather. But also, the constants compared to the time 35 years ago when the HP calculators were designed, the constants at the time were measured and somewhat independent from one another for the physical constants. This is no longer the case today because many constants now have relationships with them. So some of them are considered as being base constants, fundamental constants that are really the ones that matter. And then you have derived constants that are computed from the base constants. And so if you look there, you can see, for instance, that the Z0 constant is a computed constant. You can see the expression. So I'm going to get the value, but you can see that in the definition that is scrolling there, it's actually defined as a matter of other functions like mu0, c, etc. And now it's going to compute the value. For performance reasons, the result of this computation is cached, and so the evaluation of constants is fast in a program or when you're solving equations, but it's always computed when there is a definition from other constants. What this means is that if we have a new measurement of a constant, we just update that constant, and any dependent constant is going to be updated automatically. Now, another nice feature of the constants menu is that we have the notion of uncertainty, standard and relative uncertainty for each of the constants. So if I take the C constant, which happens to be a basic constant, so if I take the numerical value for that, this is really by definition, it's actually by definition of the meter that we have this, the meter on the second are now defined based on that precise value. And so the uncertainty for that is going to be 0. So let me go to the constant menu. And if I take, for instance, the standard uncertainty for that constant, yeah, so sorry, I need to take the constant itself. It doesn't know that it has a value now. So I need to have the constant, and I take its standard uncertainty, and the standard uncertainty for this one is 0. Now, if I take something like, for instance, the mass of the electron, this one is something that we measure, and so this one does have, this one does have a specific standard uncertainty. And I can also, so let me use the undo command to restore the one, and I can get the relative uncertainty for that value. And so you see that it's precise to roughly 10 digits. Now, there are functions that actually help you deal with uncertainty in computations. I'm not going to cover them today. They are still work in progress because we're trying to make things a bit simpler to do. The objective is to have the calculator track automatically the precision of a computation and be able to give you the exact number of digits on the output that correspond to the computation you made, based on the uncertainty that is known for the constants. So this is coming in the next release. For the moment, you have the uncertainty, but you have to do the computations of precision yourself. So I think that I covered the equation library pretty extensively, but as you can see, there's a lot of work that has been put into this, and I really have to thank Jean Wilson for his unrelenting work on adding the library, adding all the equations from the HP50 and checking the values, putting the values of the constant. Then we did many cycles of iteration to get the tests to pass. And in all this work, we found only one error in the documentation, where there is one case where the documentation seems to indicate wrong values. The calculator does not compute exactly what the documentation says. The HP50, I mean. So that's for the equation library. Now, another thing that uses the solving mechanism is the finance functions. So that's the time value of money kind of functions. And so for that, I'm going to use example that I'm going to take from, let me shift to the HP15 user manual. And let me see, time value of money. Where is it? Okay. So this chapter here tells you how to implement, using the solver to implement time value of money computations. Where is it? And so they give you various examples. So we are going to use these examples as a basis. Where are the examples? So I'm going to have an annuity with 9 months. So here's the definition. You place $155 in saving accounts, paying 5.75% compounded monthly, and at the end of nine years, how much do you get? So let me switch to the calculator there, and where is the simulator? So I'm going to use the shifts. So the blue function on the divide key, or the S key. So that's the time value of money thing, or menu. That's how we solve. And same principle as for equations, we can enter any variables and solve for any variable. So in that case, I have a number of annuities. That is, in the case of the HP15, so let me get back to the HP15 manual. So if you look there, you see that they are entering n is 9 times 12. The HP48 calculators are slightly more advanced than that, and they have a variable for the number of years. And so what I'm going to do is the number of payments per year, you see, is 12 at the moment. And so I'm going to enter, so now I'm sorry, but I have a doubt on whether I should enter 9 or 112, 108 here. I think it's 108. I think it's the number of total payments. But the payments 170 the interest rate 575 per year. Now that's annual. I don't need to divide by 12 as I would do on the HP15 example. And the amount for the present value is, so you put it in negative in that case. That's the present value. And I'm going to compute the future value out of that. And you see that I see future value is 259.74. And if I go back to my HP15 manual, that's exactly the result that I should expect there. So this is essentially the same functions as on the HP calculator. So let me find the functions that you have on the HP 48 or 50 calculator. So you see that you have TVM. You can decide whether you have TVM stands for time value of money. That's the menu that you're seeing on the simulator. And you can solve for a given variable. You can decide to have payments at beginning, TVM beg, or end, TVM end. And you can amortize for a given payment. So how many payments did you already do? So let me, for instance, look at what it looks like, what amort looks like after 12 payments. And you see that in that case, the principal is 9.5, the interest was 9.15, and the balance remaining to be paid after the first 12 payments is, so there is 164 remaining to be paid. And if I go to the end, which was 108, then the balance that's because I've set the future value at 260. So I need to set the future value at 0. And now if I do 108, yes, that's what I've paid for it. Okay, so that's the expectation. That's the result we had before. Now another thing that is only on DB48x is that I can do an amort table as well. I think that's, let me check. Amortisation schedule table. So there I'm computing the complete table where for each payment section, so let me show it, that's going to be simpler. And so you can see that I have the schedule for the first 12 payments with these parameters. So I think that's for the finance part. That's about it, I believe. And now we have a number of relatively less important features. Oh no, there is another big one that I forgot to mention, which that the root function is now capable to solve one equation or a system of equations where you can isolate one at a time, or a system of crossed equations, something that is called a Jacobian solver, where you can solve multiple equations that are interdependent through their variables. So let me give you the first example. So let me solve, for instance, sine of x equals 0.5. And I solve for x with an initial value of 0, and I use the solver, which is yellow on 7, and I use the root function here. Now, what is interesting is you see that it says x, so there is an assignment again, x equals, and then it says 30 degrees. Where does it get the 30 degrees from? Well, it's because if you look at the original here, it was able to invert, isolate through algebraic operations. It was able to isolate the value x using the isolate function. So it's essentially doing symbolic operations to be able to solve the result, and the result then uses the arcsign function, which gives a unit by default on DB48x. So that's how we get units transparently out, angle units transparently out of equations like this. Let me edit this to show that this works even in somewhat more complicated cases, where I can have 2 times x plus 1, and then I solve for interest. Oh yeah, because now it's trying to solve with units, and now it's not happy because I need to tell it that this is so let me go to the units menu, and I'm going to use the angles menu and turn that into, oops. That's an interesting bug. I was not expecting that. This is an editor bug. It's not, it should insert the unit directly. So now I'm adding 1 degree, so that I think should let it solve that correctly. So and now it's solving that properly. So again, we have something that is different. Now there is a setting that is, I refer you to the documentation, but there is a setting that says whether you're allowed to do this kind of algebraic isolation when you're solving a system like this. Now there are cases where it can't do it. For instance, if the same variable appears multiple times, so let me do something like this, sine x plus cosine of 2 times x equals 1, and solve for x. And so I need to put ticks. Now that x has a value, I need to put quotes to quote the name, and I'm going to start with initial value 0. And yeah, this was, let me find something that is a bit more difficult to solve. Now this is probably going to work, I believe, because, yeah, because now, since we have x twice, it can't really isolate x easily, and so now it has to do a numerical approximation, and it's going to solve it that way. Now, the next scenario is that we can have multiple variables and multiple equations. So for instance, I can have something like this. Let me build a list where I have sine of x equals y, and then another equation that says 2 times y is I don't know, so try to 2 times y plus times square is 0.05. I should have thought that ahead of time to make sure that this is actually solved. But so now let me solve for x and y with initial values like 0 and 0. And now it finds solutions, and as you can see, it has found a solution with the units because it was able to isolate the first one, and the second one was computed using approximations. Now, if you look at that system, it's possible here to isolate the second, to isolate y from the second equation, and then from that compute x by inverting the first equation, isolating x in the first equation. And so the solver is smart enough to do that. In that case, it detects that scenario, and it's able to optimize for that case because it's really the fastest way to solve the problem. Now, if now I change something here where I have sin x equals y, but here, instead of, now I put x. So now I have a cross between the two. And so I can't use the same strategy as before to solve it because I have x and y in the two equations. So now it's going to go into numerical approximation mode, and just because I typed it at random, I have no idea whether this one solves, but it does. And so now it's solving for x and y simultaneously, and so this is called the Jacobian solver. And it really does that incrementally, so it's going to first try to solve all the ones it can with the fastest methods, and then only what remains will be solved with a Jacobian solver if necessary. So this is really both really general and fast. Now, this covers in one function, root, which is the same that existed on the HP50G, but the HP50G would only use root for the single equation case, and then it had another command for multiple equation solver, the one that does isolation one at a time, one variable at a time. And then it had another called MSLV for multiple equations. So let me show you the commands in the manual. So we have root, which is up. So root here is solving for one variable. And then we have mroot that we saw just before. What was it? mroot here solves for one variable from using the multiple equation solver. And that in that case has to be in the AQ variable, so it's not completely consistent with the root syntax. And then you have msolve, which we just, where was it? Here, msolve, which is yet another syntax. So now it uses 3 levels of arguments, and they have to be put in arrays, and they have to be, and then it leaves the results on the stack. So the 3 versions of the solver on HP calculators do not work in a consistent way. So the choice that was made for DB48x is that root is capable of doing all 3 and detect automatically which one to apply. But there are also mroot and msolve commands that will accept an extended version of the behavior or the syntax of the corresponding command on the HP50G. Namely, the mroot one is going to work based on the AQ variable, except that now it can also work when AQ is a single function, or when AQ contains something that mroot itself would not be able to solve, and only msolve would know how to solve. And then msolve behaves like root and mroot. In other words, it can do all 3 levels, but it does it with the syntax that is specific to msolve and leaving the earlier results on the stack. So what this does is this maximizes compatibility. However, it's much simpler to use because all three commands accept the same input. All three commands will accept either arrays or lists. I forgot to mention that msolve on the HP50G takes arrays, whereas mroot takes lists. Don't ask me why, I have no idea. So in the case of DB48x, it accepts both, and it solves correctly in both cases. So overall, one of the parts that was the most complicated to remember on the HP50G is now vastly simplified on DB48x, and you can do it in any order. So that's for the solvers and multiple equation solvers. And I think that with that, we have probably covered most of the really relevant features that were added since 0.7.8, because as you can see, there is a lot of new meat. Now there are more secondary features that we are going to cover very quickly. For instance, did I think about adding them? Yes. So for instance, here in the base menu, I can enter a base number. Let me enter a number in base 2. So I don't know if you saw how many bits there are there, but if you don't know, you can use the count bits function and it tells you there are 7 bits. I hope this is correct. Well, yeah, that looks correct. So it has 7 bits set in it. Now this number was in base 2. I can set bit 3, for instance, in it with set bits. I can flip bit 3. And I can figure out which bit is the first set and which bit was the last set in that number. So these are new commands that do not exist on the HP50G, but are really practical in some computations when you're dealing with, when you're trying to do programs that manipulate binary values. Now, one thing worth noticing here is that when you enter a number in base 2 like this, so this is the syntax that doesn't exist on HP calculator, where you put the base at the front. You can use any base. Now you see that in base 2, it stayed in base 2. If you specify the base like this works for base 2, 8, 10, and 16, which have special representation that stick even if you change the base. So this means that if I shift here to binary, octal, decimal, and hexadecimal, you see that the one that had the base forced will keep its base. So this is a convenient way to have numbers that display in a specific base. But again, that only works for bases 2, 8, 10, and 16. Is there anything else? So I think that in terms of features that I can show, this is about what I can show. Other things worth mentioning is that a huge effort was made around 0.8. That was actually most of the focus of the 0.8, I'd say first half, was saving energy on physical calculators. So the battery life now lasts much longer than it used to. And that means reduced animations. There were a lot of fancy animations that are now disabled by default when you unplug the calculator from USB and when it's running on its tiny CR2032 battery. It doesn't have much juice in there, so let's save it. And in some cases, it's about 10 times more efficient than it used to be, mostly by not animating anything. And there was also a large number of optimizations, notably for matrix operations on large matrices. So this was a request by one of the users who remarked that we were barely faster than an HP50G despite, or even HP48, I think, despite having a more modern CPU. And so a lot of optimization happens under the hood to give the same results, but much faster and using less energy. I think these are the main topics since 0.7.8. So I hope that this gives you a good idea of where we stand with this project at the moment, and that we are getting quite close now to having something that is really a decent and usable replacement for our good old trusted HP50G, or so this is my HP50G here, or HP48. Where did I put my HP48? Here. Uh-oh, some tests are failing. Yeah, so tests are failing because the memory is not clean. If I don't start, so this is the HP48, and so I use these as reference now to check that I'm doing things correctly compared to existing calculators. And what you see on the screen is a number of tests checking everything there is to test about this calculator and making sure that it still works. I hope you enjoyed this long talk, and let me know in the comments if there is something you'd like me to talk about in the next iteration of these videos. Thanks a lot for listening all this time. Please put your comments, thumbs up, share, and try it on the web. Try it on your iPhone or iPad, or try it on SwissMicros calculators if you have one of them. Thanks a lot, and please enjoy.